machines installing the ribbon machine in 1926 in its Wellsboro, Pennsylvania factory. 101. The ribbon machine surpassed any previous attempts to automate bulb production and was used to produce incandescent bulbs in the 21st century. The inventor, William Woods, along with his colleague at Corning Glass Works, David E. Gray, had created a machine that by 1939 was turning out 1,000 bulbs per minute. 100. The ribbon machine works by passing a continuous ribbon of glass along a conveyor belt, heated in a furnace, and then blown by precisely aligned air nozzles through holes in the conveyor belt into molds. Thus the glass bulbs or envelopes are created. A typical machine of this sort can produce anywhere from 50,000 to 120,000 bulbs per hour, depending on the size of the bulb. 102. 103. By the 1970s, 15 ribbon machines installed in factories around the world produced the entire supply of incandescent bulbs. 104. Filament and its supports are assembled on a glass stem, which is then fused to the bulb. The air is pumped out of the bulb, and the evacuation tube in the stem press is sealed by a flame. The bulb is then inserted into the lamp base, and the whole assembly tested. The 2016 closing of Osram Sylvania's Wellsboro, Pennsylvania plant meant that one of the last remaining ribbon machines in the United States was shut down. 104. Filament. How a tungsten filament is made. Carbon has the highest melting point of any element, and in carbon arc lamps it had been demonstrated to produce incandescence fairly close to that of sunlight. However, carbon has a tendency to sublimate before reaching its melting point depending on pressure, which led to rapid blackening of vacuumed bulbs. The first commercially successful light bulb filaments were made from a carbonized paper or bamboo. Carbon filaments have a negative temperature coefficient of resistance. As they get hotter, dielectrical resistance decreases. This made the lamp sensitive to fluctuations in the power supply, since a small increase of voltage would cause the filament to heat up, reducing its resistance and causing it to draw even more power and heat even further. Carbon filaments were flashed by heating in a hydrocarbon vapor, usually gasoline, to improve their strength and uniformity. Metallized or graphitized filaments were first heated to high temperature to transform them into graphite, which further strengthened and smoothed the filament. These filaments have a positive temperature coefficient, like a metallic conductor, which stabilizes the lamp's operating properties against minor variations in supply voltage. Metal filaments were tried in 1897, 105. And started to displace carbon starting around 1904. Tungsten has highest available melting point, but brittleness was a big obstacle. By 1910, a process was developed by William D. Coolidge at General Electric for production of a ductile form of tungsten. The process required pressing tungsten powder into bars, then several steps of sintering, swagging, and then wire drawing. It was found that very pure tungsten formed filaments that sagged in use, and that a very small doping treatment with potassium, silicon, and aluminium oxides at the level of a few hundred parts per million, so-called DAX tungsten, greatly improved the life and durability of the tungsten filaments. 106. The predominant mechanism for failure in tungsten filaments even now is grain boundary sliding accommodated by diffusion or creep. 107. During operation, the tungsten wire is stressed under the load of its own weight, and because of the diffusion that can occur at high temperatures, grains begin to rotate and slide. This stress, because of variations in the filament, causes the filament to sag non-uniformly, which ultimately introduces further torque on the filament. 107. It is this sagging that inevitably results in a rupture of the filament, rendering the incandescent light bulb useless. 107. coiled coil filament. To improve the efficiency of the lamp, the filament usually consists of multiple coils of coiled fine wire, also known as a coiled coil. Light bulbs using coiled coil filaments are sometimes referred to as double coil bulbs. For a 60-watt 120-volt lamp, the uncoiled length of the tungsten filament is usually 580 mm, 22.8 in, 70, and the filament diameter is 0.046 mm, 0.0018 in. The advantage of the coiled coil is that evaporation of the tungsten filament is at the rate of a tungsten cylinder having a diameter equal to 1/8 the coiled coil. The coiled coil filament evaporates more slowly than a straight filament of the same surface area and light emitting power. As a result, the filament can then run hotter, which results in a more efficient light source while lasting longer than a straight filament at the same temperature. Manufacturers designate different forms of lamp filament with an alphanumeric code. 108. Coiled coil filament of a 200-watt incandescent light bulb, highly magnified. Filament of a burnt-out 50-watt incandescent light bulb in an SEM in stereoscopic mode, presented as an anaglyph image. 3D red cyan glasses are recommended to view this image correctly. Filament of a 50-watt incandescent light bulb in an SEM in stereoscopic mode, presented as an anaglyph image. 3D red cyan glasses are recommended to view this image correctly. Electrical filaments are also used in hot cathodes of fluorescent lamps and vacuum tubes as a source of electrons, or in vacuum tubes to heat an electron-emitting electrode. When used as a source of electrons, they may have a special coating that increases electron production. Reducing filament evaporation. During ordinary operation, the tungsten of the filament evaporates hotter. More efficient filaments evaporate faster. 109. Because of this, the lifetime of a filament lamp is a trade-off between efficiency and longevity. The trade-off is typically set to provide a lifetime of 1,000 to 2,000 hours for lamps used for general illumination. Theatrical, photographic, and projection lamps may have a useful life of only a few hours, trading life expectancy for high output in a compact form. Long-life general service lamps have lower efficiency, but prior to the development of incandescent and LED lamps they were useful in applications where the bulb was difficult to change. Irving Langmuir found that an inert gas, instead of vacuum, would retard evaporation. General service incandescent light bulbs over about 25 watts in rating are now filled with a mixture of mostly argon and some nitrogen, 110, or sometimes krypton. 111. While inert gas reduces filament evaporation, it also conducts heat from the filament, thereby cooling the filament and reducing efficiency. At constant pressure and temperature, the thermal conductivity of a gas depends upon the molecular weight of the gas and the cross-sectional area of the gas molecules. Higher molecular weight gases have lower thermal conductivity because both the molecular weight and cross-sectional area are higher. Xenon gas improves efficiency because of its high molecular weight, but is also more expensive, so its use is limited to smaller lamps. 112. Filament notching is due to uneven evaporation of the filament. Small variations in resistivity along the filament cause hot spots to form at points of high resistivity. Winking sad smiley 71. A variation of diameter of only 1% will cause a 25% reduction in service life. 70. Since filament resistance is highly temperature dependent, spots with higher temperature will have higher resistance, causing them to dissipate more energy, making them hotter, a positive feedback loop. These hot spots evaporate faster than the rest of the filament, permanently increasing the resistance at that point. The process ends in the familiar tiny gap in an otherwise healthy-looking filament. Lamps operated on direct current develop random stair-step irregularities on the filament surface which may cut lifespan in half compared to AC operation. Different alloys of tungsten and rhenium can be used to counteract the effect. 113, 114. Since a filament breaking in a gas-filled bulb can form an electric arc, which may spread between the terminals and draw very heavy current, intentionally thin lead-in wires or more elaborate protection devices are therefore often used as fuses built into the light bulb. 115. More nitrogen is used in higher voltage lamps to reduce the possibility of arcing. 110. Bulb blackening. In a conventional lamp, the evaporated tungsten eventually condenses on the inner surface of the glass envelope, darkening it. For bulbs that contain a vacuum, the darkening is uniform across the entire surface of the envelope. When a filling of inert gas is used, the evaporated tungsten is carried in the thermal convection currents of the gas, and is deposited preferentially on the uppermost part of the envelope, blackening just that portion of the envelope. An incandescent lamp that gives 93% or less of its initial light output at 75% of its rated life is regarded as unsatisfactory, when tested according to IEC publication 60064. Light loss is due to filament evaporation and bulb blackening. 116. Study of the problem of bulb blackening led to the discovery of thermionic emission, the Edison effect, the invention of the vacuum tube, and evaporation deposition used to make mirrors and other optical coatings. 117, 118, 119. A very small amount of water vapor inside a light bulb can significantly increase lamp darkening. Water vapor dissociates into hydrogen and oxygen at the hot filament. The oxygen attacks the tungsten metal, and the resulting tungsten oxide particles travel to cooler parts of the lamp. Hydrogen from water vapor reduces oxide, reforming water vapor and continuing this water cycle. 71. The equivalent of a drop of water distributed over 500,000 lamps will significantly increase darkening. 70. Small amounts of substances such as zirconium are placed within the lamp as a getter to react with any oxygen that may bake out of the lamp components during operation. Some old, high-powered lamps used in theater, projection, searchlight, and lighthouse service with heavy sturdy filaments contained loose tungsten powder within the envelope. From time to time, the operator would remove the bulb and shake it, allowing the tungsten powder to scrub off most of the tungsten that condensed on the interior of the envelope, removing the blackening and brightening the lamp again. 120. Halogen lamps. Close-up of a tungsten filament inside a halogen lamp. The two ring-shaped structures left and right are filament supports. The halogen lamp reduces uneven evaporation of the filament and eliminates darkening of the envelope by filling the lamp with a halogen gas at low pressure, along with an inert gas. The halogen cycle increases the lifetime of the bulb and prevents its darkening by redepositing tungsten from the inside of the bulb back onto the filament. The halogen lamp can operate its filament at a higher temperature than a standard gas-filled lamp of similar power without loss of operating life. Such bulbs are much smaller than normal incandescent bulbs, and are widely used where intense illumination is needed in a limited space. Fiber optic lamps for optical microscopy is one typical application. Incandescent arc lamps. A variation of the incandescent lamp did not use a hot wire filament, but instead used an arc struck on a spherical bead electrode to produce heat. The electrode then became incandescent, with the arc contributing little to the light produced. Such lamps were used for projection or illumination for scientific instruments such as microscopes. These arc lamps ran on relatively low voltages and incorporated tungsten filaments to start ionization within the envelope. They provided the intense concentrated light of an arc lamp but were easier to operate. Developed around 1915, these lamps were displaced by mercury and xenon arc lamps. 121, 122, 123, electrical characteristics. Comparison of efficacy by power: 120-volt lamps, 124, 230-volt lamps, 125, power, W, output, LM, efficacy, LM/W, output, LM, efficacy, LM/W.